We are ME452, Team 11, and this is our final presentation, analysis and redesign of the hand blender. The hand blender is a compact electrical tool for blending and puring ingredients directly into a cooking container, featuring a detachable blending wand. Various attachments can be equipped for versatility.
The total assembly consists of 10 total parts and 8 fasteners, as seen here in the exploded CAD. When the button of the top housing is pressed, the motor is engaged, which actuates the steel shaft, which spins the blade and chops the media which the blade is immersed in. Here, the exploded view identifies part numbers on this slide, which correspond to the part numbers on the bill of materials.
Our primary customers would be cooks who work in commercial and industrial kitchens because they would need to use the device for a variety of purposes for mixing, as well as the fact that they can interchange it with different types of tops that can be swapped out. Our secondary customers will be at-home cooks or amateur cooks. The only difference between them and our primary customers, who are the professional cooks, would be the fact that they would be using the cooks more for simplistic devices, and they would all probably prefer a more ergonomic design.
For our assembly sequence, we started with the bottom housing to create a solid base to build upon to increase the ease of handling. For our function component mapping matrix, we utilized the functions seen in the FAST diagram, and then we used the more detailed functions to further specify the needs of each component shown in the slide.
So looking between functions for our customer groups, so it's going to be pretty similar between mixing, containing the contents, obviously having a torque, being able to adjust the volume, and having a safe tool. Where it differs, we're going to need the ability to change tools, make it more ergonomic, be able to adjust speed. And so this obviously means there's a lot of carryover between platforms and modules, so blade guard, blades, housing as well.
In order to accommodate more models, we decided to go for a modular design. The differences between these would be the shorter blade guard and the shorter shaft. The shortened version of the main design allows for more user control with the shorter stem. And this would be the common interface that both of those parts interface with.
The product family assembly diagram shows that the assembly sequence we used is the most efficient because it splits off later in the sequence, which allows for the manufacturing processes to be the same for a longer period of time before we have to do two different processes.
Utilizing our quad chart and also calculated assembly costs, we decided to redesign the bottom housing one and the top housing. For our modified design, we were able to decrease the cost by 15 cents for the original design for manual assembly.
A design for assembly analysis for automated assembly was conducted. Through this analysis, we found that the estimation of the insertion cost was $7.20 per blender, and the estimation of the handling cost was $11.68 per blender. A sample calculation is shown on the right. This meant that the total cost per blender is $18.89.
So for our process selection for the top housing, we decided to first focus on the factors for the material, which would be ABS plastic. We chose this over materials such as aluminum and composites because of its relative cost, as well as the fact that it's lightweight. In addition, another factor that we looked at was the mass and surface roughness. These two factors would have been part of our function component mapping matrix. And for ergonomics, we want it to be lightweight as well as relatively smooth to be used and easy to operate. Based off the materials, we came up with machining, injection molding, compression molding, polymer casting, additive manufacturing, and resin transfer as our main processes that were compatible with material. And throughout the different shape, mass factors, such as shape, mass, section thickness, tolerance, surface roughness, and economic batch size, we narrowed down the process for making the top housing to be injection molding and additive manufacturing. However, we decided to go with injection molding because of the fact that additive manufacturing tends to be relatively slow. The rate it produces would not be what we want to see for the batch size, even though it's already capable of making it. And then for our process selection for the bottom housing in our next slide, We decided to use the same processes as well, such as the same material, because they're both going to be fusing together, and you don't want to fuse different types of materials together. The only difference is that there's a slightly higher mass and a slightly higher section thickness. However, every other factor remains the same. As a result, we decided to go with injection mold again, based off our previous slides.
We decided to optimize the top housing for injection molding. We ran DfM software on this part, and the following features were identified. A minimum radius at the tip of boss, the base of boss, a draft angle to be implemented on all of the bosses, as well as uniform wall thickness around the part.
The total cost of injection molding for our original top housing was 21 cents a part.
We decided to optimize the bosses that the M2 screws thread into. As you can see in the figure, the bosses have been filleted and chamfered, and a draft angle has been implemented. We decided not to tackle the uniform wall thickness due to the complexity of the surface profile and its interface with all of the other housings. There was no change with the assembly cost. This is a cross-section of one of the 4 bosses where all the changes were made. The first change was the draft angle. According to DfIM3, draft angles should be greater than 1.5 degrees and should be used in all cavities like bosses. In order to implement the change, we increased the outer diameter by 0.75 millimeters to allow for this angle, and the inner surface was chamfered at an angle of 3 degrees. The boss base radius was, according to DfIM4, should be avoided at a right angle, and a radius should be used. For this reason, the base was filleted with a radius of 1 millimeters. Similarly, boss tips should also have a radius to avoid stress concentrations, and for this reason, the tip was filleted with a radius of 0.75 millimeters.
The cost of injection molding for our modified top housing was also 21 cents. As mentioned earlier, with these changes, it allowed for a more feasible design for injection molding, as it decreased the stress concentration locations.
The second part we decided to run DfM analysis on is bottom housing number 1. We ran the DfM software on this part, and the following features were identified. Minimum radius at tip of boss, base of boss, ribs were needed to be implemented, side pulls would be required for this part, which should be removed, and uniform wall thickness should be maintained.
For our original bottom housing, the cost of injection molding per part was 27 cents.
For this part, we decided to address all the changes identified in DfM with the exception of adding ribs and implementing uniform wall thicknesses. We decided to not align all the wall thickness due to the complexity of the surface profile, and did not add ribs due to the small scale of the feature that the ribs would have been applied to. Here we can see the modified bottom housing interface with the new arches that were designed and M2 screws. The changes that were made were, number 1, the boss base radius. According to DfIM4, right angles should be avoided and radiuses should be used. For this reason, the base was filleted with a radius of 0.75 millimeters. Similarly to the boss tip radius, those should also be filleted, and for this reason, the tip was filleted with a radius of 0.75 millimeters. The largest changes that we made were in changes 3 and 4, which can be summarized in DfIM1. In order to eliminate the side pulls that were required and align all fasteners in the Z direction, we designed a new way to secure the motor. In doing this, we removed the thickest wall that the motor was resting on, and designed 2 additional arches that would instead secure the motor from the other side instead of that wall. This added 2 parts and 2 fasteners, but we decided it would be worth it in the end to orient all parts in this assembly in the same direction for the purposes of automated assembly.
With all of these changes, the cost of injection molding for our part decreased to 18 cents, which saved us 9 cents per part.
The benefits of conducting this design for manufacturing exercise was that it reduced the cost for the manufacturer and it reduced the volume of the material. We'd do this differently if we could do it again by choosing a software model that was compatible with SolidWorks, because we found it difficult to truly adjust the features of this blender to accommodate the various design changes that we wanted to accommodate.